Okay, good morning all, and thank you for joining this group colloquium at WMG. Today it's my great pleasure to introduce Professor Dierk Raabe, who is our speaker today. Professor Dierk Raabe is currently the director of the new Max Planck Institute for Sustainable Materials in Düsseldorf, Germany. He studied music, metallurgy, and metal physics. After his doctorate in 1992 and habilitation in 1997 at RWTH Aachen, he received a Heisenberg Fellowship and worked at Carnegie Mellon University. He joined Max Planck Society as a director in 1999. His main research interest today is to make industrial production of materials more sustainable, focusing on basic research where the leverage for CO2 elimination is particularly large. His specific interests lie in the sustainable metals, specifically green steel and sustainable aluminum alloys, physical metallurgy of metallic alloys, steels, hydrogen, aluminum alloys, atom probe tomography, machine learning, and sustainable manufacturing. He received the Gottfried Wilhelm Leibniz Award, Acta Materiala Gold Medal, and 2 ERC Advanced Grants. He is also professor at RWTH Aachen in Germany and KU Leuven in Belgium. He is a doctor honoris causa at the Norwegian Technical University, Trondheim. Professor Raabe has kindly agreed to present today on the topic of sustainable metals and the specific cases for green steel production. Professor Raabe, thank you very much for your time and accepting our invitation, and please proceed with your talk.
Good morning, everybody, and thank you very much, Prakash, for the very nice introduction. It's a big pleasure to be with you and talk a little bit about sustainable metallurgy. I would like to show on the first slide a bit more background about our new institute, which we have recently renamed from Max Planck Institute for Iron Research, with a more than 100 years long history, into the Max Planck Institute for Sustainable Materials. And we are currently hosting 4 departments, have about 340 people, and you also see some budget numbers there. Just to give you a glimpse of the size of the campus and of the activities here. So the topic of the presentation today is about sustainable metals, with an introduction to the topic, and then diving a little bit deeper into the case of green steel production, but placing attention particularly on aspects related to the basic physical metallurgy of this topic. And there are a couple of very fine colleagues who are in that team, particularly of green steel and green nickel production and similar topics, and I will highlight their specific contributions during the presentation. So we are on a 7 billion tons quest, and what do I mean by that? I mean by that the amount of material that we are consuming every year as a global society, and that embraces all the metals, concrete, polymers, and so on. And since that number is, of course, very big, I thought, it compares to what? And I tried to count it in terms of Eiffel Towers, but still we have 700,000 times the Eiffel Tower. So it's not really insightful. And when I picked as the next biggest player, the Burj Khalifa that you all know, it still holds for 14,000 of these buildings. So the quantity of materials that we are using to fuel and equip our societies globally is incredibly large. And our interest lies in doing some of the basic science for sustainable metals, specifically in the context of a circular economy. And the first question might be whether this, is becoming worse, or whether it's going away, or whether it's becoming better. And on this little overview diagram, I try to convince you that this problem is not becoming better, but it's becoming actually worse. Because when we look at the global distribution of wealth, and we have a rough perception about the close relationship between the consumption of materials and the GDP, and the resulting CO2 emissions, of which the materials production makes a huge chunk of, then it becomes clear when we multiply that with the corresponding GDP-related growth factors and the expected population growth, it becomes quite apparent that this will not go away, but this problem will become bigger. That means on this overview diagram, you get an impression about the fact that the consumption of materials will actually in part more than double as we go towards 2050 and 2060. That means we urgently need to develop a better understanding how we can mitigate, particularly the associated CO2 emissions. Here's an overview diagram that's getting a little bit more specific on the scope 1 and 2 and 3 emissions in CO2 to give you a rough number. And iron and steel production is the biggest culprit here, quite obviously. And chemicals, plastics as a big emitter of CO2 also. Then comes cement and aluminum and so on. And in different sources, depending how these different scopes are quantified and calculated, these numbers, of course, can be shuffling around a little bit. But the point is that iron and steel production is the biggest producer of CO2. And when we put a couple of these action items or possible research fields on the table in the context of material science for a circular economy, we have on the right-hand side, of course, topics like leveraging artificial intelligence to improve workflows and so on and make processes more efficient. And then all the indirect measures that material help us to take as materials, as sustainability enablers for the electrification, as magnets and so on. We have a very interesting emerging field of living materials and biometallurgy. For instance, as some of you know, in the field of hydrobiometallurgy, enriching bacteria, metal enriching bacteria are already used today. But then we have the hardcore metallurgy in the fields of longevity, corrosion protection, the hydrogen economy, and the materials that can withstand hydrogen embrittlement. We have the quest for what I call design of materials for infinite recycling, which means we must in the future really cope with a scrap-related higher impurity content of many metals. And that is a vastly unsolved problem and a lot to do there. And then we have the primary production, the sustainable use of all our resources in the entire material value chain. And that is due to the fact that there's no such thing as the expected growth factors that I've shown to you on the basis of scrap alone. That's not going to happen, but we don't have not enough scrap on the globe, particularly not fueling the big groups, the big CO2 producers like iron, steel, aluminum, titanium, nickel, and so on. But we need, in a global average, at least 2/3 coming from primary synthesis in the next decades. And that's where the very high CO2 emissions are coming from. So when I just summarize it very briefly as an entry on that slide, we talk about 2 billion tons of metals alone produced every year, which is good. It gives us also jobs and leverages 50% of the global manufacturing, as we all know, has a huge turnover to feed our families and so on. But on the downside, we have not just the huge industrial greenhouse gas emissions that metals are causing, but we have also these insufficient recycling rates. We use up to 15% of the global energy for making metals, and we have 2 billion tons, give and take, of waste associated primarily with the production, but also with the overburden and the tailings and so on from the mining sector. That means whatever we do is big. That means we always have a big leverage in our hand, which is good. That means the work that we try to do as a community, as metallurgists, can be potentially impactful. What is often a misunderstanding outside of the metallurgical community is that we are talking about hard to abate problems. That means we do not just use fossil fuels for heating our furnaces, but we often deal with heterogeneous redox reactions. That means they are really inherently entangled into the scenario. And they often follow elementary redox equations like shown here, where you have a metal oxide which is exposed to some kind of carbon monoxide, usually that comes from fossil fuels, of course, and that is producing carbon dioxide and leaving the extracted metal behind. So that is in principle the type of redox equation we are dealing with. So it's an intrinsic redox problem, not just used for heating. And the question now, how can you take carbon out of the bill for about 80 different metals that we produce, specifically, of course, for iron production? And we have several players at our disposal. That could be hydrogen or different hydrogen carriers or vectors, as we say. And I later come back to using ammonia as one example. Then we have Hn+, which refers to using radicals. So after plasma excitation in plasma chemical reactors, we can excite the hydrogen to enhance the reactivity and turn these redox balances into an exothermic balance. Then we can use a dirty hydrogen. That means the question is, do we always have to really use the purest hydrogen that comes from water splitting? And I'm not so sure whether this is really a good strategy. And of course, we can use electrons directly. The carbon footprint is not only gigantic for iron steel production. That, as you can see from this view graph, comes essentially only from the enormous quantities of nearly 1.85 billion tons of steel production per year. But the actual carbon footprint of iron production, as you see, is with about, give and take, 2 tons, not too big per quantity of produced metal, namely per ton of iron produced. When you compare that with nickel or cobalt or the other elements, then these numbers can be in part much, much bigger. That has, of course, to do with the strength of the chemical bond between the oxygen or the sulfur with the corresponding transition metal. But it also has to do a lot with the fact that some of the minerals, particularly those that we use for iron making, are actually quite pure. Hematite, which is kind of the standard mineral today, coming mostly in very high quality from Australia or from Brazil and so on, can have up to 70% iron as a mass content. That means it's very, very pure material of high quality. That means you really heat what you need. When we go to materials like nickel or cobalt or also copper, very similar, then these best available commercial ores that are industrially used have a very low metal content. Look here, you look at a laterite, which is a typical weathering oxide used for nickel extraction, has probably 1.3% nickel only. That means you are permanently heating and enriching material that does not contain much of what you are seeking. So that gives you only a glimpse of how complex these enrichment and extracting problems really are. And another aspect is, of course, that we do not only go to these macro scales, but we have also at the microscopic and nanoscopic scale a very strong entanglement of the elements in a product. In the laptop or PC that we all stand before now, or in our mobile phones, we have in part more than 40, in some laptops even more than 50 different chemical elements. And the point is to integrate them very highly. So obviously it is very, very challenging to get them in a clean way back from these products. This is I think, an endeavor, a quest that we are only about to begin, and the recycling quotas in the moment in this field are really tiny, practically negligible. And there's a lot to do, an area that is coined or called urban mining. Just to give you a rough flavor of what that translates to, we have from the best South African mines, we can get up to 1 kilogram of gold, for instance, from 200 tons of mineral. And we can get the same amount of gold when we extract the gold from 3 to 4 tons of mobile phones, essentially from the chips there, of course. And that applies to the other metals also. So we have very, very rich urban sources, but how to extract them in a smart way is yet to be explored in high detail. So the punchline is that many of us are aware, or the society is aware, of what is nowadays called green chemistry, to say, can we not, bring CO2 together with sustainably produced hydrogen back into the chemistry cycle, or to produce artificial fuels and so on. But I always say, what about the rest? The periodic table is much, much bigger. That means we must unfold likewise research activities that are capable of dealing with these rich research problems I try to allude to in a very brief manner in the field of green metal production. And again, when we compare that with a very nice periodic table that has been published in that paper from Warwick more than 10 years ago, we see that most of the particularly so-called high risk and very expensive metals, for instance, those that we need for making hard magnets and so on, are practically nowadays not recycled or recycled only to a very, very low fraction. That means there's a huge gap between what has to be done and what is currently industrial and societal practice. As I said already, for the bigger quantities, we could likewise state, okay, just do everything from recycling, as I just claimed with the view graph before or suggested. And then everything would be much better because the energy consumption, particularly for those metals that have a low melting point, compared to the energy, when you compare that to the energy you need to extract metals from their oxides or sulfides or carbonates, then everything would be much more sustainable already, which is actually thermodynamically completely true. But the problem is the longevity of many of these metal products, like steel and so on in buildings, can last up to more than 120, 130 years. So it means what we now put in our cities, bridges, infrastructure, ships and cars and so on, comes back with a substantial delay. But we need the scrap now, particularly also when you look at the UK situation, where now there's maybe an onset of a race to keep the scrap in the country and not export it, to turn more and more to scrap-based steel production, which is also the case here on the continent and in different countries. However, the big question is contamination. That means the quality and contamination associated with making steel from scrap brings about the challenge to turn it not just in high quality construction steel, which is doable and industrial practice today, but the real challenge is how to turn it into high value added steel products that you use for much more demanding and safety critical applications, where we talk 2 gigapascal steels and not 400 megapascal steels. And the third thing is, of course, demand and market. There's a huge gap, as I told you, that the markets are growing much, much faster than the scrap becomes available to these markets. That means we must deal with primary production in any case, because the steel markets will grow tremendously. And here's an overview over the iron scrap. And you can see that indeed, while the scrap market will indeed be growing, as you can see here, likewise, the fraction of the highly contaminated material of that scrap fraction will also grow. That means we must deal with how to cope with very highly contaminated steel scrap for high safety relevant products and high quality products. The same applies to the aluminum market, where already since more than 20 years we have a crossover, namely that the return of scrap into the aluminum smelting market is coming primarily from the post-consumer, again, highly chemically contaminated market, than from well-sorted pre-consumer scrap. So the same applies for aluminum, and iron and aluminum are very different when it comes to how they go about and how they can digest impurities. And we call that the science of dirty alloys. Of course, these alloys are in the classic sense not dirty, but it just should make us sensitive that we somehow must find scientific answers here. When we put this a little bit more academic, then we all have been growing up in a cosmos that consists of the microstructure. The microstructure is that what really leverages the well-known mechanical properties of metals and also some of the corrosion features of metals, lends them toughness, ductility, and of course strength, with all the many defects you see here and that you all know. But when I now blend into this picture the enormous contamination that I talked about coming from scrap, or in the future from low price minerals in ores from the primary synthesis market also, then I'm suddenly thrown not into the highly applauded high entropy alloy systems that are plotted here, but I'm suddenly finding myself in the corner of high dimensional phase diagrams where we mainly have to deal with 10, 15 or 20 contaminants. That means we must understand much better the borders of high dimensional phase diagrams in the future, including of course also the kinetic consequences. And this creates altogether a huge configuration space. When you just plot here the partitioning function, the Zustandssumme, then you can realize that now with all these many data points and atoms and configurations, we have a space of properties and phases that is very, very hard to conquer. Also, when you add to this the spins and all the electronic excitations. That means we must always find means of dimensionality reduction through theory, through machine learning, and so on. Otherwise, it's very hard to understand how we can conquer such a big and complex chemical space. Here is a little example that you don't think I'm exaggerating, but this is a little animation. I hope it comes across sufficiently nicely across the ether. And you see here an aluminum sample with many impurities that I have plotted as a little bit bigger, highly colored spheres, of course. And you can see that this is a highly contaminated piece of aluminum, which essentially should only contain oxygen and a bit of manganese. And that is essentially packaging aluminum that you use, to wrap your chewing gum or your chocolate. So, but it's today very highly filled with impurity atoms that you actually don't want and don't need. And when you imagine that is entering, electrical car design, buildings, safety parts, planes, aerospace parts, and so on, you better want to know what these impurities are doing to corrosion, to mechanics, toughness, embrittlement, hydrogen, embrittlement, and so on. Now, let me turn gradually more and more to the biggest culprit, the biggest mammoth in the room, and that is steel when it comes to CO2 emission mitigation. And we have a very big ballpark in which we can play, where we deal with many reduction principles, electrons, ions, protons, molecules, radicals, and so on. We have different types of feedstocks, some of which I already mentioned, from lump ores, pellets, fines, scrap, of course, but also organic waste, industry waste that we can leverage, and different type of reductants and reductant carriers, and of course different minerals with very different impurity content, for instance, to arrive at low price use of ores. And also when we have to redesign some of the reactors, why not look into their capability of using less pure iron oxides that could give you a cost advantage at some point. So in our group, we are primarily interested in working on different direct reduction techniques using hydrogen and different combinations of hydrogen and gases which contain hydrogen. We use electrons and we use plasma methods. Now let me say a few words about direct reduction, because it has probably today the highest TRL level, as you all know. And we do experiments like several other groups also, where we expose solid oxides. These are classical sintered pellets with a diameter of a little bit more than a centimeter exposed to hydrogen or hydrogen-containing gases. And that was usually done here, like in this animation from the company Midrex. They built these reactors from reforming methane. And the mixed reform gas, which also contained hydrogen, was classically used in these reactors, which, however, had only a small market share below 5%. And that is gradually changing, because you could imagine that you can operate these reactors also with higher fractions of hydrogen. And that is globally currently going on, that such reactors are designed and operated and built and so on. And the basic idea is, of course, that you then create a certain direct reduced iron sponge, and that you charge into, for instance, this smelting technique like an electric arc furnace, and then charge that further downstream into ladle metallurgy and continuous casting and so on. Now, when we take a look at such a pellet reduction here, this is such a polycrystalline pellet aggregate at 700 degrees centigrade, so a little bit lower than what you would do in such a Midrex operation. You can see on the right-hand side the kinetics, which is starting very quickly, starting with the trigonal hematite reduction into the cubic inverse spinel magnetite, which is the next oxidation level, which then further is reduced into wüstite iron oxide, and the wüstite iron oxide is transformed into alpha iron at 700 degrees centigrade. And you can see that during the beginning and the end of that reduction, you are nearly losing 1 order of magnitude in kinetics. And we are studying some of these details. Here you can see a very nice in situ SEM experiment that was done by my colleague, Professor Mark Willinger, in an environmental SEM microscope. And you can see when I play this again, how the single crystalline wüstite that we had exposed here to pure hydrogen in the microscope is overgrown by this dense layer of pure iron. So that is creating a core shell type of structure. And when we cut that through, then we see when we look at it from the side, how you have in the interior this very porous iron oxide sponge. The porosity comes from the fact that during the preceding reduction stages, you of course lose oxygen, and the oxygen loss happens primarily at the reaction interfaces, and these nano voids or nanopores are then undergoing coalescence into bigger pores. Much of that, I think, happens at the immediate reaction interface already, because their kinetic also of coarsening is highest. And you also see that when such a wüstite is towards the end of the reaction process in such a reactor, completely surrounded by relatively dense iron, here's an even higher resolution, then you can see that the kinetic bottleneck is to bring the oxygen outbound through these relatively dense iron layer to the next surface where it can react with the hydrogen to form water. Now, when we take an EBSD and phase analysis, as shown here, again at 700 degrees centigrade from the initial towards the near final state after 30 minutes, again at 700 degrees to slow things down a little bit and make them easier observable, you can see that you have an inherited porosity which comes from the sintering process, so offering free reaction surfaces. And these are, of course, also the surfaces, as you can see, where the nucleation of the incommensurate magnetite with its cubic crystal structure takes place. And you have an Avrami-Kolmogorov-like growth of the magnetite into the surrounding hematite grains. So that is kind of understandable. And the nucleation rate then depends on the available surface to volume ratio, essentially. And then you can see, however, that the next step, namely the formation of the cubic wüstite in the likewise cubic magnetite, is more complex. And I'll show you some more slides about this topic because it's really, really interesting. Because the wüstite and the magnetite are sharing the same O2 oxygen minus lattice. And that means we seem to encounter here certain reshuffling, relaxation of the iron as the oxygen gets depleted and the structure gets more elastically stressed. But this is still under scrutiny, and we intensely investigate how this exactly works, this interesting, say, decomposition type of phase transition. And at the end, you see then how the alpha iron in this already very, very porous, more than 45% porous structure is evolving from the wüstite. Here you see single crystalline area, where you see on the left-hand side, everything has more or less the same color in the inverse pole figure. We look at a single crystalline portion of a magnetite to wüstite, and you see the two faces, the orange colored magnetite here in the center and the wüstite surrounding it. And you see this blocky structure where there is kind of an isostructural transformation between the two, as I've mentioned before. And in the kernel average, you see that you also measure for the local curvature or accumulation of geometrically necessary dislocations. You get a sense of the misfit between these two phases, but otherwise they seem to be pretty coherent in part. When you go deeper into single crystal work, something that we are currently doing, that's some unpublished work, you see how very, very complicated that can become. Because even though you start with very clean conditions and very clean single nucleation, you have, like you see here on the left-hand side, the hematite, on which the magnetite is then formed, as you can see here. But the next steps are already so complex and depend so much on the evolving porosity, the locally heterogeneous nucleation and the stresses, that as further you go down into that redox sequence and transformation sequence, plus all the enormous stresses and defects, that this microstructure gets more and more complicated, even though you started from a very clean single crystal. So whatever you start off with, you're ending up like in a real mess. And when you look into the texture and the coherency and the crystallography, we are only about to begin understanding what the role of these features for the overall transformation and of course for the mass transport of the oxygen would be. And also these types of pictures show you, of course, or give you a flavor of how close this is to the physical metallurgy we all grew up with in the area of steel or titanium and so on, or in superalloys. So some of that is really related, and that's why I find it so encouraging also to recommend these topics to younger researchers who like complex phase transformations. But as I said, we do not only have transformations, we also have very complex defects and crack formation. We have delamination, and I'll show you a few here. Here, for instance, you can see that in some areas, indeed, the wüstite is, as I said, surrounded by very dense layers of ferrite. But you can also see in this diagram that you have delamination, maybe enhanced also by hydrogen, that we don't know, where you then, like here and here and here, create also new fresh surfaces where the reduction can go on. That means it's also from the defect, damage, and transport side a very heterogeneous scenario where the porosity does not only come from the mass loss, but also from damage and fracture. We try to put this into a phase field simulation that you can see here. That means we take such patches and solve the transport and the Cahn-Hilliard and the Allen-Cahn equations for these phase transformations. I cut that here a little bit short. When you want to go deeper into the phase field simulation, I would be happy to discuss that with you after the presentation. But the point is that you can essentially, by fitting the iron oxide, so the wüstite to iron transition in a corresponding Landau functional form, and solve the Cahn-Hilliard and Allen-Cahn equations. And then you can also, for very heterogeneous scenarios, predict where the iron is formed, and you see substantial deviations from the classical core shell of models. But as I said already, we also have to account for elastic stresses. That is something where the classical models do not include this effect. And here we did a couple of phase field calculations where we started just in a pure elastic version. And we made our life in the beginning very simple by translating the loss of oxygen to a corresponding displacement field from which you can calculate the displacement gradient, which in turn, when you feed that into the Hooke's law, gives you an elastic stress. And you can see here with more than 5 gigapascal locally, these stresses are of course far too high. That's not realistic. So we have also changed our phase field calculation into an elastoplastic form so that we cap beyond a certain elastic stress the response into inelastic elastoplastic response, as you see here. And then you can reach stresses of 0.5 megapascal about in the oxides and in the iron also, and that is much more realistic. It also helps you to make predictions about the dislocation content, because that is a feature that might be very important for discussing the role of dislocations, for instance, for the mass transport of oxygen or also of iron. So the knowledge about defects like free surfaces, cracks, and dislocations is very important, and that's why we are doing these types of simulations. Here you can see the increase of the porosity now back to a commercial pellet, again at 700 degrees centigrade as a function of reduction time. And you can see that the porosity starts from the inherited one from the sintering, like 27%, and ramps up to more than 40% towards the end of the reduction due to the mechanisms that I have explained to you before. Now, when you break these samples and look at the topology and distribution, you see that you have very coarse porosity, and some of these coarse pores being also connected, forming complex channel patterns. And you have also very fine pores, as you can see. So it's like a Swiss cheese, but much, much more complicated. And that is extremely important to understand the mass transport and the water formation in these commercial pellets. And I think here we are only at the beginning of understanding of how these pellets should be sintered and how the porosity should be evolving and what the different gas compositions in the reductant affect regarding the porosity and their connectivity regarding the kinetics of the reduction and the capturing and the storage or release of the water as a redox product. So this is really interesting science that's still going on, and I share just some of the pictures that we currently subject to corresponding topological analysis. Here is from our colleagues with whom we collaborate at Shanghai Tech University of Dr. Chen and Professor Wang, a very nice in situ observation with a dense solution holder where you can work under very high near ambient pressure conditions here with 10% hydrogen in the holder in the early stage, namely from the transition from the hematite to the magnetite. Let me play that movie again. We are still about to analyze this in detail, but you can see there's really an explosion of these nucleation sites during this transformation. When we carve out some of the stills to show better how these patterns are evolving, you can see here as we ramp up the temperatures, how complex and how multifold the nucleation events are and how quickly you're losing the mass and open up massive porosity. And we study this also under these in situ conditions up to very high resolutions to better understand how, for instance, the formation of the nanovoids is formed and how they are percolating or connecting and so on, because we think understanding the kinetics of the connectivity of these pores as they are formed might play a very important role for the removal of the water. Why is that so important? Here you see a few tomographic nanoporosity analysis, as you can see here, that we have done with tomographic electron microscopy to better understand how they are really connected. And on the right-hand side, you see again one of our phase field calculations after or during the cooling down process. That means after the reduction, when the material cools down, and you see on the right upper hand side that some of the water has indeed been captured by some of these pores. And that leads indeed to the reoxidation of the inner perimeter of these pores, which we could also then prove and find in electron diffraction experiments, as you see on the left-hand side by my colleague Red Zhou, who is an Alexander von Humboldt fellow here in our group. So that plays a certain role. Then we went even down further to the scale of the atom probe. And here you see an experiment that was done by Ayman El-Zoka together with Se-Ho Kim and Baptiste Gold. And we cut out a wüstite single crystal with an apex curvature around 50-55 nanometers, exposed it to deuterium, so to labeled hydrogen, to, so to say, do a steel factory, direct reduction steel factory directly at the atomic scale. And the result is shown here in a short form. You see on the inside of that partially reduced tip, you have the iron oxide surviving. So we interrupted the process by purpose. And you see in pink colored here, the surrounding pure iron single crystal. And you can see these droplets of water colored here by this yellow envelope. So that gives us a better insight, and when I maybe can run the movie, a better insight of where and how the water is formed and stored inside of the material at a very, very early stage, and how it is connected to the formation of the pores. By the way, when you do that here with the atom probe, you know you are chemically very sensitive. That means you can also better learn and understand how this is related to the presence of gang elements, to impurities, like sodium, potassium, and other elements that are highly attracting the formation of water. So there's also an intricate interplay between the local chemistry and the accumulation of water inside. Now, one little sidestep is, as I mentioned in the beginning, the use of other vectors. Here we use, for instance, ammonia to reduce iron oxides. And ammonia is here, of course, a carrier, not the complete reductant, but we extract the hydrogen in the reactor. That means we don't use a splitter, but we exploit the fact that iron, once it's formed, is a very efficient catalyst to split ammonia into nitrogen and hydrogen. And then you go through this autocatalytic reaction where the more iron is formed, the quicker the transformation of ammonia into nitrogen and hydrogen works, and you use then the hydrogen to reduce the iron. And you do all in the same reactor. And the reason was that the ammonia is much easier and at much lower cost to transport than hydrogen. As we all know, you only need something like minus 37 degrees centigrade to liquefy it. So it's much more cost efficient than doing that with hydrogen. And there's an established, of course, international trading system with 180 or 175 million tons of ammonia created every year already. So it's established workflows and transport pathways. So we get, a very nice pure iron reduced sponge material. We thought in the beginning, as you see from this nice EBSD map. But when you start to look into the nitrogen signal in the EDIX, then you see that, oh gosh, there's a lot of nitrogen obviously in the sample, although the material is split at about 350 degrees centigrade. So you have pure hydrogen and nitrogen, these temperatures. But indeed, when you go to the atom probe analysis and do phase-sensitive EBSD analysis, as you can see on the right-hand side, you form up to 35, 40, 42% of nitrites. So a very high nitrite fraction. Now, this was first, of course, a disappointment. But on the other hand, when you charge these nitrites due to the high vapor pressure of the nitrogen to an electric arc furnace, the nitrogen is evaporated and you get pure iron, which you again can charge into subject to lead metallurgy. So it's in principle all good and fine. It was just interesting to go through the details and the surprise. And now we are looking also into which kinds of nitrites are formed here, because the nitrites are, of course, interesting by themselves. As a totally separate route, a quick glimpse into our hydrogen plasma-based smelting reduction methods, where you in principle use a plasma torch or plasma arc furnaces to make the hematite liquid. The melting point of hematite is only a little bit higher than this of iron. And then you have a permanent stirring of this ionic liquid, exposing always fresh oxidic melt to the reaction interface with the free hydrogen-based radicals, giving you a very, very efficient reduction, as you can see here on the right-hand side. And due to the more than factor of 2 higher mass density, the metal sinks down and allows you to do very nice hydrogen-based plasma smelting reduction with an arc furnace without any direct reduction. And we also do many types of hybrids between the two. That means we reduce only some portion of the material in a DRI technique and subject it then to plasma arc smelting and so on. So there are many hybrid technologies that you can use here. One more example where we use plasma reduction, also for many other metals, is also for waste in the context or with the ambition of having something like a zero waste concept for material extraction. And we use red mud, as you know, a famous debris from the Bayer process for the enrichment of the aluminum oxide from the bauxite mineral, another weathering ore, which is very rich in titanium oxide, silica, and particularly in iron oxide. And this has piled up to the enormous mass of more than 4 billion tons of the planet. It's highly alkaline and very toxic material. And the magnitude is shown here. You have a typical, storage area where this red mud is stored, in part for enormous costs exceeding those of CO2 penalties by far. And you see, compared to the pyramids of Gizeh or Golden Gate or Wembley Stadium, that these are really, really huge, huge ponds. And we do the same thing, as I said before. We charge the red mud into a plasma smelter with only 10 or even less % partial pressure of hydrogen. And we indeed can extract the iron content from this toxic red mud in a single extraction run. That is shown here on this overview diagram. We can also use a neutralized oxide for construction materials, but particularly we were able to extract the iron nodules from this toxic waste. And we have now the first collaborations with industry going on because they have to pay so much money for dumping this red mud, and there's still so much valuable material in it. So that is another just quick example. And the last example I want to share is what we call one-step metallurgy from ore or from oxides to alloy. And that goes back into our textbook understanding that we have the 3 main steps in our field of metal extraction, the usually liquid alloying of things to make the actual alloys out of the different metals that we extracted, and then subject everything to thermomechanical processing to really leverage the cosmos of our microstructure features to arrive at the desired bulk alloys with their specific microstructure and properties. And we have replaced now these 3 steps by a single reaction step. And several groups have also before us looked into this alternative. And what we have done here is we mix several oxide in the appropriate stoichiometric fractions and do the hydrogen-based direct reduction plus the mixing plus the densification and pore closing and so on. And to some extent, depending on material, also the microstructure design in one single reactor step. So that is in principle sounds like a very trivial undertaking. And it brings about a couple of examples. That means you can do everything at low temperature in the solid state. You have a single reactor. You don't need to include any fossils and have, of course, smaller capex requirements and so on. And you can arrive at, decent sized, in this lab scale experiments, a decent sized sample sizes. And we have chosen a very simple example, namely a nickel iron alloy, namely the famous Invar alloy, to demonstrate that this really works, plus the densification. And you can put this a little bit on a thermodynamic pressure map where you show here one axis, which is the iron plus the other element mixing enthalpy that tells you whether we talk more about compound formation or phase separation, which is both an adequate target. It just shows you where you should end up thermodynamically. And it shows, of course, the delta G of the oxide minus that for the water to show you whether it can be reduced under these hydrogen-based driving forces. And you can equip that further, of course, with certain kinetic playground laws to say, what can I do in terms of temperature and time to arrive at something like desired microstructures also. What was interesting to see when you go into the detail here in the synchrotron analysis, that when you have only iron oxide and nickel oxide in the oven, it is not so that you reduce thermodynamically, of course, nickel oxide first into pure nickel, and then the iron oxide is waiting to be reduced as a second compound into pure iron. No, that's not happening, but what is happening is that the iron oxide, once the nickel has been extracted from the nickel oxide, starts to partition into the freshly formed metal. So that is seen in terms of the lattice parameter. Here from the synchrotron data, you can clearly see how the lattice parameters change. It means the nickel is directly forming an alloy while you still deal with iron oxide. That means we see that here the nickel oxide is shown here. And then you have the first steps from the hematite transitioning into the magnetite. But as soon as the first nickel is formed here, you can see that these little yellow droplets, the iron actually starts to partition into these nickel areas, forming directly the iron nickel alloy. So the kinetic reaction pathways are different than what we thought, and that's quite interesting, and we look also deeper into that. So I stop here, and I thank you very much for bearing with me. And just as a last slide, I wanted to show that when we look at these gigantic steel factories, now the new ones coming in form of DRI reactors or other reactor concepts and so on, there's so much science for all of us to do, from the macroscopic reactor transport, chemical engineering side down to phases microstructure analysis, electron microscopy, EBSD analysis, micromechanics, because all these transformations come together with very high stresses, the theory of phase transformation, and even the electronic base understanding of the elementary interface features and the transport coefficients. So thank you very much for your attention.
Thank you, Professor Raabe, for a wonderful talk. And any questions to the speaker?
Hi, Dirk. Thank you very, very much for the talk, and fascinating. I guess that there is absolutely, as you say, so much that can be done. What I think the biggest question that I have is really thinking about how we cope with the increasing demand in countries like India in particular, and what would you say would be the best route forward in a country such as India with growing demand, not the sources of scrap that we might have in Europe, as to the route forward to mitigate CO2 emissions in that kind of economy?
Yeah, thank you very much, Claire. That's a wonderful question. I hope you can hear me okay?
Yes, thank you.
Okay, good. So I think that's indeed a wonderful question, which I think is very often overlooked in the general discussion. As you already alluded to, we indeed have very local solutions, to our several companies where we have places with more or less scrap and different quality of scrap and so on. And that is in Europe maybe more mature and better to handle, and also maybe easier to create business models, at least for currently 5 to maybe 15% of the market for such sustainable products, where the customer also gives us in part the somewhat higher price for these products. But indeed, as you say, that's not really where the CO2 is coming from in the moment. It's coming from, as we know, more than half the production is China, and likewise India is starting, as you correctly say, from 120 million tons or something like that per year, and the Indian government is planning to ramp them up towards 500 million tons or 450, something like that. So that is indeed the punchline, and that is going through blast furnace at the moment. So all the big players in India put all their money into blast furnaces. So that means, to answer your question, I think these big number discussions from the scientific and engineering and CapEx perspective must circle around blast furnace technology. And we know there are different techniques that are being discussed also by the Indian colleagues, and they can include things that of course have been already tried out around the globe and also in India, like feeding much higher fractions of waste materials, of polymer waste materials, of rubbers. That is already done since long for price reasons into blast furnaces. Then the other thought is what some companies have tried and are trying to increase the fraction of hydrogen, and others say hydrogen carrying gases from different industries, by the way, not just out of the steel industry itself, not just from reforming, but also maybe from future plasma lysis processes where we produce maybe solid carbon from methane reforming. Is another avenue that I find very attractive, because carbon is not bad, but carbon dioxide is bad. So solid carbon is actually even a product, and that has to be also been channelized into according business model, and companies look into that. And the last big thing I find very exciting to think, let's look into the coke. When we take the total coke fraction in a blast furnace, maybe 80% of that we need for heating, and maybe at most 18 to 20% for the stoichiometry as a reductant. And that means, can I reduce the amount of coke required for the heating by other means of heating the blast furnaces? But then you must replenish, of course, that that percolation, that content that allows for gas percolation in this blast furnace. So you might have to replace some of that coke with something that is inert, and then maybe pump gases into the blast furnace. So there, I think I see in the literature 5 or 6 different strands into which the research on blast furnaces is going. But I think that's exactly spot on question.
Thank you very much. Yes, I was going to say, I find it very interesting because I've been talking to people who talk about things like use of biomass, and you go, great in principle, but equally translating that globally to the countries that need the alternate fuel sources are not the ones that are going to have the access to something like biomass. And so I think one of the biggest points I think I'm still learning is this need to be able to look at different solutions for different places, taking into account, as you've been mentioning, the business models and the supply chains, as well as the technical answers to it. And I think that I hope that we don't move away where there is real strength in some of the research activities from being able to consider the blast furnaces, because I think that's on a global scale, that's a disadvantage if we move away from trying to optimize that as well.
Yeah, I totally agree with you, because I think we don't help anybody if we go into the thin ice of a pony farm discussion where we pretend everything is green when we use scrap and so, but on a global scale it's not lining up. The sheer numbers do not allow to discuss that in that way. And I'm totally on your side. We must look into all these directions, and particularly into the big numbers when we really talk CO2. The thing, however, that I always, and that we as a community pledge for, is to not forget the basic research. Sometimes when I talk to some of the colleagues, you get or decision makers, you get the impression that you can buy all of that just on the market. And that is, as we all know, is a mistake. If you don't understand, what the right pellet design is, the right blast furnace technology of the future is, you must model all these things. We know how complicated a multi-scale model of a blast furnace is. When I now start changing things, taking things out, I must put all of that in, very complex simulations and so on. And I think that's why I'm, as a scientist, quite enthusiastic. You don't know where to start. And when we entangle that or fold that with the magnitude of the CO2 mitigation, then we have so much to do. And I think our job must be to definitely communicate that also to decision makers and agencies, because when you talk to them, oh, I work on a blast furnace, they fire you. I mean, that's, and so we must really make sure we do a good marketing strategy to explain people, if you want to solve these problems, blast furnace must be included.
Yes, I absolutely agree. I think it is that realistic, trying to get people. I see it particularly when you talk about the policymakers. I think you're absolutely right. I find that a lot of them are very insular looking rather than outward looking in terms of global context. And I agree with you. It's our role to try and get the right balance. There's not a single answer, and get the balance.
Yeah.
Thank you very much, Dirk. Really enjoyed it.
Thank you, Claire. Thank you.
Yeah, Peter, would you like to ask your question?
Yeah. Hi, Dierk. Yeah. Thank you for a very nice presentation.
Hi, Peter. Thank you.
You showed that you made your reduction. Some of the slides were 500 degrees, but your main slides were reducing at 700 degrees. But when going industrial, aren't you going to a higher temperatures to speed up the kinetics? I have seen typical 900, but where do you think we should land?
Yeah, it's totally correct what you say. The 700, we do it by purpose to be slow, and hence, make all these pellets and samples accessible to a very detailed analysis. We can interrupt and control the processes at these low temperatures. But you're totally correct. Many of the DRI concepts will end between something like 830 and even above 900, because many of these ovens have enormous gradients, and some of the temperature and reaction gradients are not yet well understood because they depend highly on the gas mixture that you fuel, because hydrogen is per se an endothermic redox reaction and not an exothermic one. And hence you must co-fuel and must understand how these gradients, lead to different structures, kinetics, and then also to different heating and gas formation in these big reactors. Now, when the biggest ones that are now commissioned are above 1 million annual tons, so these are really big machines. And so you're totally right, temperatures will be much higher, but within the furnaces, I expect gradients of more than 100 Kelvin in the same machine, in the same cross-section even, in different parts of the oven. So, but you're right, this is more for academic purposes. The other thing is, of course, when you go to high temperatures, you must really carefully study at what point you transition to gamma iron formation, because then the transport coefficients will drastically change.
So you have to stay below 911.
Not necessarily. When you can do the reduction towards the FCC iron formation and tolerate the sluggishness of any transport coefficient in them. On the other hand, when you have sufficient fresh surface by fracture, damage, or by the high kinetic speed, high stresses break it up, then you are doing fine because things are localized at the fresh interfaces. But when you are surrounded, depending on what exactly your gas mixture is, you can sometimes have a very dense core shell structure. Then this would slow you down quite enormously.
Thank you.
Thank you, Peter.
Thank you. Any other questions?
Yeah, can you hear me?
Oh yes, yeah, please.
Hi. Good morning, sir. First of all, it was a very insightful talk. I just wanted to ask one thing. The problem with Davis also pointed out in a country where steel production is heavily dependent on the blast furnace route. Earlier I was working with one of the steel making company in India, Kalyani Steel, and they actually were also the blast furnace based steel making facility. I just wanted to ask, what is the state of, the like some of the salts are also coming where there is a permeable membrane made of perovskites and everything, which can actually convert carbon dioxide into carbon monoxide, which can be fed into the blast furnace for reduction, which is not which doesn't leave the footprint. So there are some composite absorbance as well, which can actually store CO2, which is being produced from the blast furnace. So how is the state of art of this particular section where the where the storage of CO2 or the potential conversion of this into carbon monoxide could be done?
Yeah, that's an excellent question indeed. And I left that, of course, totally out. And that is also not my area of expertise. But you're totally right that the CCS and the CCU, exactly as you mentioned, standing for carbon capture and storage, and
Yes.
carbon capture and utilization are, of course, additional escape routes for large-scale blast furnace operators to mitigate the total net CO2 emissions. And that's also being done by several companies. And they do it differently with different concepts. We have here some companies who already try to ship the CO2, for instance, to the North Sea and Atlantic to pump it into the empty methane regions under the sea. But one thing is the total carbon capture storage volume on the globe will long-term or even mid-term not be sufficiently high. That means that can be a short-term solution and, of course, ramps up the price of your steel product quite enormously.
Yes.
That means, again, you can fuel by that, offer such steels only to 5, 10, or 15% of the customers, not to the others, which pay you whatever 15 or 20% higher price for the steel. And the second thing, as you already said, the much more sustainable solution long-term is obviously carbon capture and utilization. And exactly as you said, that starts with filtering out and separation. The biggest problem are not CO2 or other gases. The biggest problem of such machines is that they are highly mixed and also the gases are highly contaminated. And as we all know, the classical use of membranes or catalysts or MOFs and so on is in such environments, it's the right approach. We must look into this. However, the contamination destroys them very, very quickly. That means I think a lot of research is needed in these areas, exactly as you say, of the utilization of these waste gases. But this is associated with a very high selectivity, as you also mentioned, with membrane technologies. And so everything we have are very robust catalyst or throwaway low price catalyst or catalyst made from waste and so on, to at least do a little bit of conversion with the CO2 midterm and maybe all of it long term. I think you're totally correct. Otherwise, there's no way out.
Yes. Thank you. Thank you.
Thank you.
Thank you.
Thank you.
Any other questions? If not, Dierk, I have one very quick question. I know that most of your work you do for academic purposes using extraordinary kits of microscopy, atom probe, all that. How much of this work is actually being funded by the industry and shown interest from the industry participants? I know that academically you have published a lot of good papers, reviews, all that.
Yeah, so regarding the industrial collaborations, I would typically not rather unfold with whom we collaborate here or so, but with some companies around the globe, we discuss these topics. And others maybe are not so academic in their endeavors. And so I would say when it comes to sustainable alloy production, the fraction of research funding, let's put it that way, to be kind of polite here, coming from the steel sector is normalized by the amount and so on is by far the lowest. So I think the research funding that comes from other metal groups like aluminum, nickel, and even titanium in this area is much, much higher. So I think in the iron steel industry, you all know it's a lower price product compared to the other metals, but I think a lot more could be done and funded. But yes, some companies do fund research.
Okay, great. Thank you. One last quick question, if no one is asking. If I see the whole alternative making of the sustainable iron making, what I see is basically replacement of carbon as the reducing agent with either hydrogen or plasma or ammonia, all that. So other than this, for example, if you produce hydrogen cheap, is it very simplified the problem that we can achieve the green steel, or do you think still we have any big challenges?
No, I think I think the biggest challenge is a little bit like Claire had mentioned. We in the greenest and best of all worlds, we would build DRI machines, many DRI machines or plasma machines or related technologies that make use of hydrogen as a reductant, plasma or molecular form, and buy the sustainably produced hydrogen and do that, carbon-free reduction. However, that is not lining up because you would need something between 250 million and 300 million tons of hydrogen every year out of this sustainable production. And we all know this green hydrogen is not existing, not in these quantities, and definitely not at this price. I don't know whether we currently stand at, $5,800 or so at ton hydrogen, green hydrogen, and so on. So the costs are enormous and the availability is simply not given. And that is indeed the reason why in the next decades, where the mitigation of the CO2 problem is the most important one, we must find other solutions where the hydrogen could come from, or how we produce the hydrogen from more conventional technologies where we, however, capture the CO2 or produce solid carbon. That means I'm always a bit careful of promising anybody that the world will be nice and green because every gram of steel will be produced by green hydrogen. That's not going to happen in the next decades. There's not enough. That means we must look into all the other opportunities that I mentioned, including other ways to produce hydrogen, and we look into some of these techniques. It's just a little bit too early to present this in a talk. But I think your question was again spot on. That's one of the big transition challenges.
Thanks a lot. Thank you very much. I know we already passed 5 minutes after 11. Oh, just quickly.
Yes. Good afternoon. Sorry, just my screen. Very interesting talk. It's not my field of expertise, although in the nitrogen, the nitriding, I would be interested, just out of scientific curiosity, what would happen to the slag, because this is a method to make silicon nitrides, aluminium nitrides. Did you look into this?
Yeah, we started I had that only on one slide because my talk was anyway already a bit too lengthy, I'm afraid. So indeed, the reaction products that contain the nitrogen are for us very interesting because you find many transition nitrides, not just the stoichiometry. Exactly, there are different combinations where the nitrogen is combining with the iron oxides in different stoichiometries and structures, and with the iron in different transient form. We only started to look into this, so we don't have a dedicated postdoc working on that, but we see by that yes, you can use it also for alloying indeed, and that's something we look more into. But it's simply we have probably no funding to look deeper into this, but this material is very, very rich in different nitrogen-containing compounds. And we were really surprised. It's more plasma synthesis, if you want. No?
Yes, indeed.
It's very, very interesting stuff.
Yeah, I agree.
Yeah, we have seen that directly. I totally agree to you. It's definitely not just a simple nitride. It's much more complex.
No. Especially with ammonia. Yeah, it's known as a nitriding agent. Yes.
Yeah, it's a really fun game. Yeah, yes. But for this, I definitely need funding to have a postdoc doing this, because I think it's a very rich source for research, I think.
Oh, yes. I did my PhD in that direction. That's right. Thank you very much.
Yeah, good observation. Thank you.
Thank you. I'm aware of the time, so once again, I take this opportunity to thank Professor Raabe for this wonderful talk, and thank you all for joining the talk, and have a nice afternoon or morning, wherever you are.
Okay, thank you very much again for having me. It was a big pleasure, and thanks for the nice discussion.
I recorded this lecture, and probably I share with you the link. Okay.
That would be nice, and maybe I can show it around here also. Thank you.
Yes. Thanks a lot.
Thank you very much. Thank you.
Bye-bye. Bye-bye, Claire. Bye-bye.
Thank you.